We're going to break this problem up into a bunch of different parts because it can get pretty complicated towards the end, but this one is relatively simple. We're going to begin with the expectation value of x of position. And of course, we're going to go ahead and write it out in the most general way possible, where we have the position operator right here sandwiched in between the wave function and the complex conjugate of the wave function here, and then integrate that over all space. And of course, the interesting thing whenever we do it, as the problem describes, using the ladder operator, the position operator can be expressed in terms of ladder operators in this way right here, as described by the textbook, where this is the raising operator and this is the lowering operator. And of course, if you read in the textbook that comes from the factorization of the Hamiltonian. So if we go ahead and substitute this in, and again, like the rest of the problem, I'm going to go ahead and just write the indefinite integral as a substitute for the integral over all space. So I'll go ahead and put brackets here because we already have some parentheses here to keep the bookkeeping a little bit easier. So of course, let's go ahead and write it out. Okay, now let's go ahead and write our wave function. Okay, so now that we have the wave function here, we can go ahead and pull the constants out in the front here and then distribute this wave function in onto these operators right here. So let's go ahead and perform that. Okay, so now in this step, we're going to go ahead and evaluate these operations that get done here. And of course, in the textbook, we've already found these out, where the raising operator acting on some arbitrary nth state is equal to the square root of n plus 1, and then that state raised by 1. And then the lowering operator acting on some arbitrary nth state is equal to this, where it just lowered the state here, and then it has some value, square root of n out in front. So if we go ahead and put these in, and again, I'm just doing this to save time here. And you might already be able to tell with this operation performed, when the complex conjugate acts on these two values here, the overlap between the nth state and the nth plus 1 state is 0, and the overlap of the nth state and the n minus 1, the next lowest state, is equal to 0 as well. So by orthogonality, this whole term is equal to 0. So the position operator, or the expectation value of the position, is equal to 0 for some arbitrary nth state. And that makes sense if we go back and look at the different plots for the wave function of the simple harmonic oscillator. They're all going to be relatively symmetric about the center line, the x equals 0 boundary. So this actually does make sense, even though 0 is not necessarily always a measurable value that we can attain for position for the simple harmonic oscillator.